You were taught that math builds on itself. First numbers, then algebra, then geometry. And for most people, that worked fine until calculus. Calculus is where students who were great at math suddenly feel lost. Not because they aren't smart enough, but because nobody explained what calculus actually is before throwing formulas at them. By the end of this video, you will understand exactly what calculus does, why it exists, and how it works. No formulas yet, no memorization, just the real idea explained clearly from the beginning. Here's the one sentence that explains all of calculus. Calculus is the math of things that change. That's it. Everything in calculus comes from two questions. First, how fast is something changing right now? Second, how much has something changed in total? Those two questions have names. The first is handled by something called a derivative. The second is handled by something called an integral. You will understand both by the end of this video. Now here's why this matters to you. Almost everything in the real world changes. Prices change, speeds change, temperatures change, your phone battery changes. Regular math, the kind you learned in school, is good at handling things that stay the same. If you drive at a steady 60 miles per hour for 2 hours, basic math tells you the distance, 120 miles, simple. But what if your speed changed the whole time? What if you sped up on the highway, slowed down in traffic, and stopped at red lights? Now, basic math can't give you an exact answer, calculus can. That's the problem calculus was built to solve, math that works when things are always changing. Before we get into the two main tools, you need to understand one idea that makes all of calculus possible. It's called a limit. Let's start there. Here's what a limit means. A limit is the value that something approaches as you get closer and closer to a specific point. This matters because it solves a problem that shows up constantly in calculus. Sometimes you can't calculate the exact value at a point, but you can get closer and closer to it. A limit tells you what value you're heading toward, even if you never technically land on it. Here's a concrete example. Open Google Maps and zoom in on a curved road. Keep zooming. The more you zoom in, the less the road looks like a curve. Eventually, it looks like a straight line. The road didn't change, but the closer you look, the straighter it appears. A limit works the same way. You're asking, what does this approach as I zoom in forever? The key point here is this. A limit is not about where something is. It's about where something is heading. That difference is small, but important. Keep it in mind. You'll need it. Here's what's actually happening when mathematicians use limits. They're describing behavior near a point, not necessarily at it. This is how calculus handles situations where the exact value is impossible to pin down directly. Here's what rate of change means. It's how fast a quantity is changing at a specific moment in time. This matters because knowing how fast something is changing is often more useful than knowing what it currently is. You don't just want to know your phone battery is at 40%. You want to know if it's dropping fast or slow. That tells you how much time you have left. Here's the concrete example. Your phone shows 40% battery. But is that 40% going to last 2 hours or 20 minutes? The battery percentage alone doesn't tell you. The rate tells you. If your battery is dropping 2% per minute, you have 20 minutes. If it's dropping 0.5% per minute, you have an hour and 20 minutes. That rate, 2% per minute or 0.5% per minute, is exactly what rate of change measures. The key point. Rate of change is always about one specific moment, not the average over an hour, the exact rate right now. Here's what a derivative is. It is the mathematical tool that calculates the rate of change at any point. This matters because once you have a derivative, you can find out how fast something is changing at any exact moment, not just on average, not just approximately, but precisely. Here's the example. Imagine you have dash cam footage of a car trip. You pause the video at exactly 3:42 p.m. The car is moving. What is its exact speed at that frozen frame? Not its average speed for the trip, not its speed a minute before or after, its exact speed at that instant. A derivative calculates that. It takes a function, a mathematical description of how something changes over time, and gives you the exact rate of change at any point you choose. This is the important part. The derivative is not a single number. It is a new function. It tells you the rate of change at every moment, not just one. So if you have a function that describes your car's position over time, the derivative gives you a new function that describes your car's speed at every single moment of the trip. The key point, the derivative turns how is this changing overall into how fast is this changing right now at this exact moment. Here's what accumulation means in calculus. It is the process of adding up infinitely many small pieces to find a total. This matters because many real-world totals can't be calculated by simple multiplication. They have to be built up piece by piece, moment by moment. Here is the example. You go for a workout. For the first 10 minutes, you're walking low intensity, burning maybe 4 calories per minute. Then you jog for 20 minutes, medium intensity, burning 8 calories per minute. Then you sprint for 5 minutes, high intensity, burning 15 calories per minute. Your burn rate changed constantly throughout the workout. To find the total calories burned, you can't just multiply one number by the total time. The rate was different every minute. You have to add up what you burned during each small chunk of time. That process, adding up all those small pieces to get a total, is accumulation. And when the rate is changing continuously, calculus gives you the exact way to do that. Now here's why this matters to you. Almost every real quantity is built up through accumulation. The total distance you drove, the total water that filled a tank, the total money earned when your hourly rate changed. These are all accumulation problems. The key point, accumulation is the mathematical process of building a total from many tiny, constantly changing pieces. Here's what an integral is. It is the mathematical tool that calculates accumulation. This matters because just as the derivative gives you an exact tool for finding rate of change, the integral gives you an exact tool for finding totals, even when the rate of change is different at every moment. Here's the example. It rained all day yesterday, but not at a steady rate. In the morning, it drizzled. It was about 0.1 inches per hour. In the afternoon, it poured, about 0.8 inches per hour. In the evening, it lightened back up to 0.2 inches per hour. How much total rain fell? You can't multiply 0.1 inches per hour by 24 hours. The rate wasn't constant. You have to add up all the rain from every small window of time throughout the day. The integral does exactly this. It takes a function that describes a changing rate and calculates the total amount that accumulated. Visually, you can think of it this way. If you draw a graph of the rainfall rate over time, the integral calculates the area underneath that curve. That area represents the total rainfall. The key point, the integral answers the question how much in total when the rate of change is never the same from one moment to the next. Here's what the fundamental theorem means. Derivatives and integrals are opposites of each other. This matters because it connects the two halves of calculus into one complete system. You don't have two separate tools that happen to be useful. You have two tools that are mirror images of each other. Here's the example to make this concrete. Think about addition and subtraction. They are opposite operations. If you add 5 and then subtract 5, you end up right where you started. Multiplication and division work the same way. They undo each other. Derivatives and integrals work exactly the same way. If you take a function and apply the derivative to it, you get a new function. If you then apply the integral to that new function, you get back to where you started. They undo each other perfectly. Let me show you exactly how this works with the car example. You start with a function that describes your car's position over time. You take the derivative, and you get the function that describes your car's speed at every moment. Now, you take the integral of that speed function, and you get back the position function. Position to speed to position again. The derivative and integral cancel each other out. The key point, the fundamental theorem is the discovery that the two big questions of calculus, how fast is it changing and how much has it accumulated, are actually two sides of the same coin. Now let's look at how these 6 ideas fit together as one system. It starts with limits. Without limits, derivatives are impossible. A derivative is calculated by asking, what does the rate of change approach as the time interval gets smaller and smaller? That's a limit question. Limits are the foundation that everything else is built on. Once you have limits, you can build derivatives. Derivatives answer the question, how fast is this changing right now? They work at a single point, a single moment. Then there's the parallel track. Integrals answer the question, how much has this accumulated in total? They work across a span of time or distance, and the fundamental theorem connects those two tracks. Like, it shows that derivatives and integrals are not separate inventions. They are inverse operations, two ways of looking at the same underlying relationship between a quantity and its rate of change. Here's the way to hold it all in your head. Limits make it precise. Derivatives measure the instantaneous. Integrals measure the cumulative. And the fundamental theorem shows they are the same process running in opposite directions. Let's talk about what most people get wrong when they first encounter calculus. These mistakes are common, and knowing them in advance will save you a lot of confusion. Mistake 1, confusing a limit with the actual value at a point. A limit tells you what a function is approaching, not necessarily what it equals. These can be different things. A function can approach a value without ever reaching it. When you see a limit, always ask, what is this heading toward? Not, what does it equal right here? Mistake 2, treating dx as just 0. In calculus notation, dx shows up constantly. Many students read it as an infinitely small number, which is basically 0, so I'll ignore it. This is wrong, and it causes major errors. dx represents an infinitely small change, not 0, but closer to 0 than any number you can name. It still participates in the math. Ignoring it breaks the calculation. Mistake 3, memorizing formulas before understanding the ideas. This is the most common mistake. Students are handed derivative rules and integral rules and told to practice them. They can pass a test by memorizing, but when a problem looks slightly different, they freeze because they never understood what they were doing. Understanding the concept first makes the formulas obvious. They stop feeling like arbitrary rules and start feeling like logical consequences of what you already know. The fix for all 3 mistakes is the same. Go back to the definition. What is this tool actually doing? What question is it answering? When you know the answer to those questions, the formulas are just shortcuts, not mysterious procedures you memorized. Here's where calculus shows up in the real world. Places you interact with every day, GPS and navigation. When your phone tracks how far you've traveled, it uses an integral. Your speed changes constantly. You accelerate, brake, slow for turns. The GPS integrates your changing speed over time to calculate the total distance traveled. Medical dosing. When doctors calculate how a drug moves through your body, they use derivatives. The drug concentration in your blood changes over time. The derivative tells doctors exactly how fast the concentration is rising or falling at any moment, which determines when to give the next dose. Machine learning and AI. Every AI system you interact with was trained using calculus. The training process uses derivatives. Specifically, it calculates the derivative of an error function to find out which direction to adjust the model settings. This process, called gradient descent, runs millions of times to make the model more accurate. Finance. Compound interest, in the interest you earn on your savings account, is an accumulation problem. Your balance grows at a rate that changes because the interest is always being added to the total. An integral describes exactly how that balance grows over time. Your phone battery. The estimated time remaining on your battery is calculated using the current drain rate, a derivative. Your phone measures how fast the battery is dropping right now and uses that to predict how long it will last. Calculus is not a subject you study and then put away. It is running in the background of the technology you use every day. Let's bring this together. Calculus is the math of things that change. It was built to answer two questions that basic math cannot handle cleanly. The first question: how fast is something changing right now at this exact moment? The tool for this is the derivative. It gives you the instantaneous rate of change at any point. The second question: how much has something accumulated in total when the rate was different at every moment? The tool for this is the integral. It gives you the total amount by adding up all the small pieces. These two tools are connected by the fundamental theorem of calculus, which says they are opposites. They undo each other, just like addition and subtraction. And underneath all of it is the concept of a limit, the idea that you can describe what something is approaching even if you can't land exactly on it. Here are your three takeaways. 1, when you see a derivative, ask how fast is this changing right now? 2, when you see an integral, ask how much has this built up in total? 3, when you see both in the same problem, remember they are inverse operations. One undoes the other. You now understand what calculus is, not the formulas. Those come later, but the reason the formulas exist, the questions they answer, and the logic that connects them. That understanding is what makes everything else learnable.